Section 12.2 is going to discuss 3 by 3 systems of equations. Now the way that gets its name is, first of all, we've got 3 equations, and secondly, we've got 1, 2, 3 unknowns. Generally speaking, in order to solve a 3 by 3 system of equations, or to solve any system of equations, you're going to have at least as many equations as you do unknowns. That's typical. Not always the case, but sometimes the case, often the case. In this case, we've got a 3 by 3 system of equations, and they ask us whether or not this is a solution. One thing you have to realize about this is that this represents the variables x, y, and z. It's an ordered triple. Sometimes I like to call them 3 tuples. But in any case, if this is going to be a solution, how do you think I could verify that? How do you think I could check that, yeah, this is actually a solution to this system of equations? Let's worry about finding the solution later. How would you figure out that, yeah, that's a solution? Yeah, plug them in. It should work in each of these equations. In other words, if I plug in -1, 3, -2 into this equation, I should get -1 on the left-hand side, which would match what I have on the right-hand side, and so on. -1, so let's put a little question mark there as I plug in -1, 3, and -2. And let's see if that first one works. So it's going to be -2 plus 3 plus 4 equals -1. That looks like 5 equals -1. And I don't think 5 equals -1. So this is not a solution. So not a solution. We'll take a look at what that means geometrically in just a minute. Right now, let's take a look at the next one and see if this is a solution, -2, 0, 7. So we'll plug that one in, see if that's a solution. So again, I like plugging these things in with parentheses. So -2, 0, and 7. So it's going to be -2 plus 0 minus 14. It's going to be -16 equals -16. That checks. Up here we weren't sure, down here we're sure. Let's try it in the next one. So I want 2 times something plus 2 times something again. I want that to equal 10. We'll plug in that -2, 0, and 7 into the middle equation. -2, 0, and 7. There's no place to plug in the y. And we end up with -4 plus 14. 10 equals 10. So again, looking good. Now, is it enough just to do 2 out of 3? Are we good? All right. Getting a few looks saying, no, we got to do all 3. And you're right. You got to do all 3. See if the last one equals -6. So 3 times -2 plus, or excuse me, minus 0, and that does equal -6. So -6 equals -6. This is a solution. -2, 0, 7 is a solution. Now, back when we were dealing with 2 by 2 systems of equations, life was a little bit easier in terms of the geometry. When we were dealing with 2 by 2 systems of equations, then we had several things that could happen. Let me remind you of the geometry in the 2 by 2 case. So let's just draw a couple quick graphs here and remind you of the things that could happen in the 2 by 2 case. The ideal thing that we would like to happen is we wanted to see 2 lines cross each other. So you'd have, for instance, this line and this line cross each other like that, and then Great. What was your solution? Your solution is this point right here. And if we had something like that, we had a consistent. Does anyone else remember what I said about this one? Consistent and independent. Well done. Consistent and independent. Now that's the nice thing that can happen. There's one solution. Let's take a look at what else could happen. Well, you could have something like this. One line looks like that, and another line looks like that. Now what's going on with this one? What would we say? Is this the one a consistent solution? Is this a consistent system of equations? Yeah, well then that one's inconsistent. So inconsistent. How about independent or dependent? It's also independent because the lines are just different lines. And the last thing that we can have going is something like this. All right. I think getting the laptop on a pink marker here. That one and this one. What's going on here? Your two lines are essentially the same. Now I didn't have any solution here, so 0 solutions. How many solutions do I have here? An infinite number of solutions. How would I characterize this in terms of dependent, independent, consistent, and inconsistent? Yeah, perfect. Perfect on both counts. Consistent and dependent. All right, so those are the three things that can happen in the 2x2 case when you have two equations and two unknowns. But the geometry gets a little bit more complex when we're talking about the 3x3 case. So this is our 2x2 case. Reminder. In the 3x3 case, you're no longer dealing with just lines in the plane, you're dealing with the entire plane. So I'm going to go to something that does much better than my drawings could do, and that is, let's look at something like this. These are pictures of some planes. And you can think of the walls, the floor, and the ceiling of this room. Is there a way for all three of those, or three of those, to meet at one point? What would it be? What combination of the walls, the floor, and the ceiling in this room could meet at one point? Could somebody direct a finger at that? Where would that be? Alex? Yeah. Gavin? Yeah, the corner. The corner. And that's what you're seeing right here, is that those three planes meet at one point. Now, like I said, the geometry gets much more complex. So that's a way that you can have exactly one solution. How about B here? How many solutions do you think I'd have at B? If I took, for instance, the front wall, the ceiling, and the projector screen, that'd be three planes that can meet along a line. How many points, how many solutions do you think I would have here? Let's look back at this here. How many solutions did I have here? Infinitely many. It's going to be the same thing here. You're going to have an infinite number of solutions. Now, there's other ways that you could fail to have a solution. So here's a few examples of inconsistent systems of equations. Notice that in all three of these situations, I'm not getting a single point that's on all three of these planes at the same time. The geometry is getting much more complex. But the bottom line is that you're still going to have three possibilities when you end up solving here. And this is what you should look out for. You should look, hopefully you get one solution. Sometimes you won't get any solutions. Sometimes you'll get an infinite number of solutions. It's just going to depend on the particular case that you're working with. And even I can't look at most of these equations and go, oh yeah, you're going to get one, none, or infinitely many. So You're going to do more work with this in college algebra, but it's a good foundation to look at some of this stuff here. So let's look at these things, figure out how to solve them. Now we've looked at a couple where we actually just check these, but how do you actually find whether or not, or how do you find those numbers in the first place? So let's start out with example B, and let me kind of give you a rough guide of what we're going to do to solve these things. So what I'm going to do is I'm going to pick one of these equations, and I'm going to use it to eliminate a variable from the other two equations. So kind of our method or our approach is pick an equation and use it to eliminate a variable from the other two equations. That's the big first step. And then from there, you're going to solve that remaining 2x2 system of equations. So if you've eliminated a variable from the other two equations, in example B, for instance, I'm going to use the first equation to eliminate the x from the second two equations. That's going to give you a 2x2 system of equations that you can solve. So solve the remaining 2x2 system of equations any way you want. And then finally substitute and solve for the remaining unknown. Substitute and solve for the remaining unknown. Okay, so that's the game plan. Let's put it in action, and we'll do that with example B here. So what I look for when I say I'm going to use one equation to eliminate a variable from the other two, try and find something that has a coefficient of 1 or -1 to use for your elimination. Now, there's a lot of good choices here. You don't always have to choose the first equation. You can choose a second or a third, and you can reorder the equations. It doesn't matter what order you have these things in. So let's take a look at this first equation. If I'm going to multiply this by something and add it to the next equation to eliminate that 2x, what should I multiply by? -2. Perfect. So let's take -2 times row 1 and add it to row 2. So that's going to be -2x minus 2y minus 2z equals -8. Added to 2x plus y minus z equals 1. Okay. What equation pops out when I add those together? Someone help me?
Y equals -7.
-y minus 3z equals -7. And you just leave that one there for the moment. I'm not going to touch it just yet. I got to do the same thing, except I want to eliminate the x from the third equation. So I'll do -2 times row 1. This time I'm going to add it to row 3. So again, that's going to be -2x minus 2y minus 2z equals -8. This time I'm going to add it to 2x minus 3y plus z equals 1. And I'm going to get something a little bit different. I'll get negative 5y minus z equals negative 7. The big thing to notice is that I got rid of the x from both of these equations. This is now reduced down to something that we solved last week. Well, actually 2 weeks ago, because it was before our Thanksgiving break. Negative y minus 3z equals negative 7. Negative 5y minus z equals negative 7 again. Here's your 2x2 system of equations. Feel free to solve this any way you want. You could solve this in 3 different ways we've discussed in this class. Do you remember any of them? What are the different ways we could solve this by? Elimination, good one, yeah. Substitution. Bonus points for the last one. Yeah, time's up. Graphing. You could graph this and solve it graphing. Now, we don't use substitution very often, so maybe I'll practice with a substitution. What I'm going to do first is I'm going to multiply this equation by negative 1. Can anyone tell me why I might want to do that? Multiply that equation by negative 1. Yeah, let's get rid of the negatives. So that's going to give me y plus 3z equals 7. And from there, I can solve for y pretty easily, right? I can just move the 3z to the other side. Y equals 7 minus 3z. Great. What am I going to do with that now? Yeah, we're going to take that and plug that expression into here and solve for y, or solve for z actually. So it's going to be negative 5 times 7 minus 3z minus z equals negative 7. Let's see what happens when we do that. And yeah, I just won't get any fancy. I'll just do negative 7 minus 3z. So it's going to be negative 35 minus, actually plus 15z minus z equals negative 7. All right. Combine like terms here. I get negative 35 plus 14z equals negative 7. If I add 35 to both sides, I get 14z equals 28. So what does z equal? Thank you. Z equals 2. Great. So 1 down, 2 to go. Z equals 2. Let's circle that. How does that help us out? Now we got z equals 2. Do I got to go through this all over again to find maybe the y and the z or the x? Manny? Yeah, plug it in up here, right? We know y equals 7 minus 3 times z. That's not too bad. Just plug in the 2. So I get y minus y equals 7 minus 3 times 2. So well, I'll just plug in the 2. Yeah, I don't want to do it this way. 3 times 2. So that gives me y equals 1. Great. 2 down, 1 to go. How am I going to find the x? What do I have to do to find the x? Yeah, you got to go back to one of the original equations. You got to have an equation that has an x in it. Plug it in there. The first one looks pretty user-friendly, so it's x plus y plus z equals 4. X plus y plus z equals 4. If I plug in 1 for y and 2 for z, then I'll end up with x equals 1. 1 and 2. Yeah. So it's x plus 3 equals 4 or x equals 1. Great. Now, one thing that you can be a little bit lax on in the test is if you circle your answers like this, I'll be really happy. But WebAssign is going to want your answers typically in ordered triples. It's going to want it written like this. 1, 1, 2. Yeah, I know. Sorry. You know. Yep. Yep. So that's what WebAssign is going to want.
At least it still makes sense.
Yeah, that's the WebAssign answer. On the test, I'll be happy with this. But what would you think? Is this consistent or inconsistent? Yeah, it's consistent. We found a solution. So once you find a solution, it's a consistent system of equations. So looking good on that one. Now to recap, let's take a look at what we did. This is the important step, is getting rid of a single variable from both equations. Once we did that, then we had a 2x2 system of equations that we could solve. Solve that any way you want. We chose to do the substitution method. I did that just for variety, because most of the time I'm going to find elimination pretty convenient. Once you find one of those values, plug back in, solve for the other one, and then plug back into one of the original equations to solve here. How could I check this answer if I wanted to? Mackenzie, what do you think you could do? If I was looking at that going, I know this is going to be like a 10-point problem. I don't want to make sure, or I don't want to make a mistake on this. How could you check your answer? You can plug it into the original system equations. Make sure it works. This is a pretty juicy problem, so when you're all done with it, just take a minute. Look back here and make sure you got it right. All right. Let's do another one. Let's try example C here. So x plus y plus z equals 4. X minus y plus z equals 2. And x minus y minus 2z equals -1. Now I want to do something rather than just always use the first equation and eliminate the x's. So, just for variety, I'm going to eliminate, something else. Now, with this system of equations, almost everything has a coefficient of 1 or -1, so it's going to be easy to manipulate and eliminate. I still like working with the first equation when it's convenient, so I'm going to work with that one. I often circle it. One important note here, you're going to use that equation twice. You're going to use it twice to eliminate variables from the other two. This time I'm going to eliminate the y's. Looks like it's pretty easy to eliminate the y's, right? You just got to add the two equations together. It helps me if you kind of show me what you're doing. It helps me give you more partial credit in the case that you make a mistake. All we need to do is add the two rows together. X plus y plus z equals 4. X minus y plus z equals 2. When I add those together, I get 2x plus 2z equals 6. And just leave it. I know there's a common factor of a 2 that we can get rid of, but don't worry about it right now. Let's work on row 1 plus row 3. X plus y plus z equals 4. X minus y minus 2z equals -1. What equation do I get? 2x perfect. Are we okay with that? If you get this far, then you've gotten kind of over the hard part. So try and get through this step. All right. Now let's take those two equations and two unknowns and solve them together. So I've got 2x plus 2z equals 6, and 2x minus z equals 3. This one we could easily do with substitution. You could just move the z over here and the 3 over there, and you have z equals 2x minus 3, and then solve it by substitution. I'm going to solve this anyway, or let's see, I'm going to solve this by the addition method. So if I want to solve this by the addition method, does anyone see an easy way I could do this by the addition method? There's a couple, really.
Multiply the bottom by 2.
Yeah, multiply the bottom by 2. That's what caught my eye. Because if you multiply the bottom by 2, then you'll have a negative 2z that you can add to a positive 2z, and that'll cancel each other out. If you wanted to cancel out the x's, you could multiply either of these equations by negative 1. And that would cancel out the x's. So let's go with the original suggestion, though. Multiply the bottom one by 2. So I'm going to take that. I don't understand why this dries out so quickly. Take that and multiply by 2. And that's going to give me 4x minus 2z equals 6, added to 2x plus 2z equals 6. 6x equals 12. And there you go. X equals 2. Great. How am I going to figure out what z is then? I know what x is. Does that help me figure out z?
Yeah, you can go to the 2x minus x, 2x minus z equals 3.
Sure. Let's plug that in here. So 2 times 2 minus z equals 3. So it's going to be 2 times 2 minus z equals 3. What's wrong with this guy? It just really ran out of ink fast or something. Anyways, I get 4 minus z equals 3. If I switch these around, they're going to change sides and change signs. I'll end up with 4 minus 3 equals z. So 1 for z. Great. 2 down. 1 to go. All right. Thanks so much, Kez. Someone else. Don't make Kez do all the work for us. How are we going to find that last variable? How are we going to find what y equals? Substitute it in the first equation? Sure. You can actually substitute in any of these equations, but the first equation does look kind of like the friendliest. So it's going to be x plus y plus z equals 4. And if I substitute in, I'll have 2 plus y plus 1 equals 4. We'll do it this way. 2 and 1. So it gives me y plus 3 equals 4, or y equals 1. Yay!
Consistent.
Yes, well done. Yeah, it's another consistent system of equations. Now, for WebAssign, you're going to have to write 2, 1, 1. Your 3 tuple. On an exam, as long as you circle all 3 answers like that, that's fine. You look back at that, or I can look at that and find that, that's fine. It is nice if you do this too. I'm not going to worry about that. How are we looking on these first 2? Doing all right? Now, let me share with you something that I use when I grade your exams. Now, when I grade your exams, I have the right answer. But when I look at your work, if you end up with something that isn't the right answer, I always try and figure out, well, where did you go wrong? Where I start is right here with your 2x2 system of equations. So our answer, 2, 1, 1, should actually work in this system of equations. If you check it out, 2 times 2 is 4, plus 2 times 1 is 2. 4 and 2 gives you 6. It works there. It works here. So whatever mistake might have been made would have been after this point. So when you're doing your homework and you do one your first try on WebAssign, and you're like, oh, I didn't get it right. You want to look back and figure out where you got wrong. Take the answer, put it in here. If it works, then your mistake is further on down the road. If it doesn't, then your mistake was getting here. All right, but figure out where you went wrong when you get these things wrong. It'll help you out for the exam. Okay, let's keep going. Let's take a look at example D. They're going to get a little bit harder here. So we've got 5x plus 4y plus 2z equals negative 8. 3x plus 4y minus 3z. Is that negative 48?
Yeah.
Thank you. And then finally, 2x minus 4y minus 7z equals negative 32. Ew. How come this one looks harder than the last one?
Numbers with the variables.
Yeah. We don't have a bunch of coefficients that are all 1 or negative 1. It's not as easy to figure out, well what am I going to use to eliminate one from the other? So what would you do? Is there something here that looks like, well, okay, we can eliminate this? What's looking good? Yeah, the y's are looking good, right? I mean, they're all either 4 or negative 4 for a coefficient. So I'm going to break with what I've done with the previous couple, and I'm actually going to use the bottom equation here to eliminate the variables from the other two. So let's circle this one to begin with. I'm going to use this equation to eliminate the y from the other two. And the reason I'm choosing this one is all I have to do is add the third equation to the first equation. Add the third equation to the second equation, right? When you do that, those 4 y terms are going to cancel each other out. So let's see how that's going to shape up. And let's see, I'm not going to try and squeeze all it in. So it's going to be row 3 plus row 1. Now my convention when I do this is the row that I add to, that's going to be my new row. That's more of a heads up for stuff later on. So 2x minus 4y minus 7z equals negative 32 added to row 1, which is 5x plus 4y plus 2z equals negative 8. So let's add that together. And we get 7x minus 5z equals negative 40. Okay. Leave that one alone for just a minute. We've got to do the same thing to the second equation. We're going to get row 3 added to row 2. So 2x minus 4y minus 7z equals negative 32 again. This time added to 3x plus 4y minus 3z equals negative 48. Let's combine those. I get 5x minus 10z equals negative 80. Okay. I've got two equations and two unknowns. Let's put those two together. So on this one and this one, we're going to solve that as a 2x2 system of equations. So it's going to be 7x minus 5z equals negative 40, and 5x minus 10z equals negative 80. what are your thoughts in terms of solving this? What would you do? I mean, there's several things that I see, but what would you do? You can use substitution, you can use addition. Elimination is the same as substitution. So what works for you? Elimination? Okay. Now, I guess I'm a little bit kind of beside myself on this one because it looks really tempting to say, all right, well, there's a common factor of 5. I could divide everything by 5 and make this equation a little bit more user-friendly. But at the same time, boy, elimination, all I got to do is multiply this by -2, right? If I multiply this by -2, then I'll have a 10z here. I can add it to what I have down here, and bam, looking good. So, I don't know. I'd probably go with multiply this by -2, the top equation. But this is kind of a nice intermediate goal. If you get here on your exams, that's, you know, some good partial credit. Even if you make a mistake the rest of the way, some good partial credit. This is your 2x2 system. So to solve that one, I'm going to take and multiply the top equation by -2. That's going to give me -14x plus 10z equals 96. I'm going to add that to 5x minus 10z equals -80. Something looked wrong.
Yeah, I think you put 48, but it was 40.
Was it 40?
Yeah.
Oh, okay. All right, thank you. 40 here? I was looking at that going, well, wait a minute. All right, so 40 here, and then...
No, yeah, that was 40.
Oh, that...
7x minus 52, so 5z is 40, or -40, not 48.
Oh, -40, okay. All right. All right, thank you. -40. Let's see, and then multiply that by -2, so that'd be -80. Positive 80, yeah, thanks. Man. Thank you for checking me on that one. All right, so that's going to be -9x equals 0. Well, that's kind of cool that we came up with this, because a lot of times people get really nervous when they have 0 as part of their solution. Like, whoa, wait a minute. How do I solve here?
Isolate.
Got to isolate the x. And to do that, I can divide both sides by -9. What happens when I divide 0 by -9? What do I get? 0. So x equals 0. Okay, nothing wrong with x equals 0 as one of your solutions. Nothing wrong with that at all. If x equals 0, I can plug that into one of these other equations. Let me plug it in here. So 7x minus 5z equals -40. I'll plug that in. You get 7 times 0 minus 5z equals -40. -5z equals -40. Gives me z equals 8. So 2 down, 1 to go. Last one to solve then would be, oh, where is it? Let's go up to, I don't know, top equation. Why not? Everything's all positive up there except the right-hand side, so does it really matter which equation I choose from the original 3? No. Good job. You could solve for y in any of those 3 equations. We're just happening to choose the first one. So plugging in 0 for x and 8 for z, I end up with 4y plus 16 equals negative 8. Subtracting 16, I end up with 4y equals negative 24. So y equals negative 6. Yay. Whew. All right. George, what do you think? Is this system of equations consistent or inconsistent? Nice, consistent. Beautiful. What makes it consistent is that we found at least one solution. So if you find at least one solution, great, you've got a consistent system of equations. If not, then, well, okay, sometimes other things can go wrong. So let's try a couple more here. Let's move on to let's see. Example G. I know I'm not doing everything in between, but I got to leave a little time for us to cover section 12.2. So, example G. 3x plus 4y plus z equals 42, and x minus 2y plus z equals negative 16. And finally, 2x plus y plus z equals 21. Okay, looking good there. For variety, again, let me just kind of bounce things around. I'm going to pick the second equation and use that to eliminate a variable from the other two equations. The only thing I really want to illustrate is that when you're choosing an equation to eliminate, it's usually easiest to choose something that has a coefficient of 1 or negative 1 for the variables. I'm just mixing things up instead of choosing always the first equation or third equation. Chose the middle equation. Now, with this equation, it's easy to eliminate either the z or the x from the other two equations. Now, any preferences? Eliminating the z or the x? Yeah, z looks easiest, right? Because you just got to multiply by negative 1. So Stephanie, if I multiply by negative 1 times row 2 and add it to row 1, what's that negative 1 times row 2 look like?
Negative
Mm-hmm.
negative z equals positive 16.
Perfect. And we're going to add that to 3x plus 4y plus z equals 42. Thanks, Stephanie. And let's see, I'll end up with 2x plus 6y equals 58. And just leave it there. You need to get to the point where you have two equations and two unknowns first. Let's try that same game for the next one. So negative 1 times row 2 added to row 3 this time. Negative x plus 2y minus z equals 16. 2x plus y plus z equals 21. This time when I combine this, I get x plus 3y equals 37. Great. Solve this any way you'd like. Let's put those two together and come up with our 2x2 system of equations. So I want that one, and I want to put that one together. So my 2x2 is going to have 2x plus 6y equals 58. X plus 3y equals 37. And that's my 2x2 system of equations. At least get this far. That gives me something I can give you some concrete partial credit for. Your choice. Substitution or addition. What works good for you? Substitution? Okay. So to me, I think it looks easiest to solve for x and then substitute that expression into y. So that's one way. Is there another way? What if you had your graphing calculator available to you on the exam? Is there anything you could do to... Okay. Well, let's see. Tell you what, I know you wanted to do the substitution method, but what I'm seeing is that if I multiply this bottom equation by -2, I get some nice cancellation. So I'm going to do it this way. I'm going to multiply that bottom equation by -2, and let's see what happens here. So I'll end up with 2x plus 6y equals 58, and add that to -2x minus 6y equals -74. Alex, help me out. What equation do I get out of this? Maybe start on the left-hand side. What do I get? 0? Yeah, 0x plus 0y, or just 0, equals what? -16. You guys got that in high school, right? That 0 equals -16? Somebody along the way told you that? Yeah, okay, good deal. All right. All right, well, 0 doesn't equal -16. Well, now what do we do? What do you think is going on? Ah, it's inconsistent. If you actually graphed those two equations, like I did here, what are you seeing from those two equations that catches your attention?
Parallel.
They're parallel. They never meet. So there's not going to be a solution there, and that means there's not going to be a solution to this system of equations. So when you get a false statement, and I want to emphasize that's false, then what you should realize is that, okay, that's telling me I've got an inconsistent system of equations. Done. That's it. Can't go any farther. There's no solution. Even if I wanted one, couldn't make one up.
So if we did another method, we would still get to the same conclusion?
Yeah. If you solved for x, moved it to the other side, and then substituted back in for x, you'd have 2 times 37 minus 6y. You'd have a minus 6y and a 6y that would cancel. You'd end up with, let's see, 74 equals 58. So it would still lead you to the same conclusion. And this is what I try to emphasize in section 12.1, is that when you get something where all the variables drop out and you have a false statement, that's an inconsistent system. If they drop out and you got a true statement, then that's a dependent system. So there's different things you can do depending on that. Let's look at example H. (0.1x minus 0.3y plus 0.4z equals 0.9. 2x plus y plus 2z equals 5. And 4x minus 5y plus 10z equals 23. Should I put this one on an exam? Does that one look like a good, fun problem?
No.
No? What if can somebody articulate what about this problem looks like? Oh, God, it just looks like a mess. Yeah, the decimals. Yeah, those don't look fun. But here's the thing. You don't have to work with the decimals. Exactly. I'm going to multiply by 10. So if I multiply everything by 10, there's a That's a marker that works. If I multiply everything by 10, then yeah, now I get something that's a little bit more manageable. What equation would that be? What equation am I going to get?
X minus 3y plus 4z.
Perfect. X minus 3y plus 4z equals 9. Now I don't have to mess with these other equations. I'm okay there. Keep in mind that if you had fractions instead of decimals, you could do the same thing. You can multiply by the lowest common denominator to get rid of the fractions. You don't have to in this case. We're all good. 2x plus y plus 2z equals 5. And 4x minus 5y plus 10z equals 23. You could use the first equation and eliminate the x's, or you could use the second equation to eliminate the y's. Those would be the easy choices in terms of elimination. Any preference? What equation and what variable should we use to eliminate? X's? All right. X's work out pretty good. I mean, it's convenient when you can just use the first equation and eliminate the x's, so I like that choice. Carl, what would I multiply this by to eliminate the x down here?
Minus 2.
Yeah. So negative 2 times row 1 added to row 2. Negative 2 times that's going to be negative 2x plus 6y minus 8z equals negative 18, added to 2x plus y plus 2z equals 5. Well, 7y minus 6z equals negative 13. And just leave it. Just leave it. Don't worry about it until we get rid of the x from the other equation. Iris, what do I have to do to get rid of the x from that third equation? Perfect. Thank you. So negative 4 times row 1 is going to be negative 4x plus 12y minus 16z equals negative 36. Add that to 4x minus 5y plus 10z equals 23. This time I get 7x minus 6z, or excuse me, 7y minus 6z equals negative 13. All right, well, let's put those two equations together. Yeah, they're kind of looking familiar, aren't they? 7y minus 6z equals negative 13. And 7y minus 6z equals negative 13. I did not make a mistake in my arithmetic here. Those are the two equations we got. Before I finish this, does anyone want to make any predictions? What do you think is going on with this system of equations? Say again? Yeah, it's going to be a dependent system. Watch what happens. So here's your 2 by 2 system of equations. Again, this is really what you want to get to. There's your 2 by 2. If I wanted to solve this by maybe the elimination method, I could multiply the top equation by, say, negative 1. And that would give me negative 7y plus 6z equals 13. And then add it to this equation, which is 7y minus 6z equals negative 13. Bless you. Hi. What would I get when I add these two equations together? Start with the left-hand side. 0. How about the right-hand side? 13 and negative 13? 0. So 0 equals 0. Wow. 0 equals 0. Well, 0 equals 0, that's true, right? But all the variables have dropped out. So as Heba was predicting, it's a dependent system. And that's the big difference between this one and the last one. The last one, when we tried to solve here, we got something that was false. This time we're getting something which is true. So this is a dependent system. Now in college algebra, you're going to have to go a little bit farther than this. But for right now, for this class, that's good. We're golden. We're done. But look out for that when you're solving your systems equations. A lot of times the problem will say, solve it, or state that it's inconsistent or dependent. So one of those two could happen. Just kind of depends on what's put in front of you in terms of a system of equations. Whew. Comments or thoughts on that one? All right. Let's call it a day for section 12.2.